Okay, so let's continue with the second part. Yeah. Okay, first of all, in general, we know this. If a divisor is less than equal to another divisor, then this implies that L of D1 is a subspace of L of D2. Okay, and omega of D1, it goes the other way around. Yeah, contains omega of D2. I believe so. Now, let's see. Yes. I mean, the proof of this mini statement is the following. Of course, we have this. So let F, so proof of this little statement there. So F belong to L of D1, right? If and only if divisor of F was D1 is bigger than or equal to 0. Of course, this implies that divisor of F plus D2 is also bigger than or equal to 0 because D2 is bigger than or equal to D1, right? If this is positive, so you just add something positive to it, and that's going to be it. Okay, so this implies that, of course, F belongs to L of D2. Oh, fine. And then for the second one, omega belonging to omega of D2, let's say, what does it mean? It means that divisor of omega minus D2 is bigger than or equal to 0. So this implies that divisor of omega bigger than or equal to D2. Well, what is D2? Is bigger than or equal to D1, right? D1. So this, if you take these two together, so this implies that omega belongs to omega of D1. Okay. Yeah. So I didn't do much. I just proved some small statement that we need. So now apply this. To D1 equal to D and D2 equal to obviously D1 D plus Q. But Q is the divisor of a point which is with weight 1. So this means just obviously, I mean D2 bigger or equal to D1, obviously, right? If you do that, then you get the two things that we wanted to prove, the ratios. Now what we want to show, actually dimension of the quotient space, namely, okay, so this quotient L of this is bigger than, so it's, yeah, L of D divided by L of D plus Q over C. We want to show that dimension of this vector space is less than or equal to 1. Why is that, right? Okay. So to do that, pick a local coordinate to prove this. Pick a local coordinate, I mean a coordinate Z at Q, or the holomorphic coordinate Z at Q. Let M be order of D at Q, which is some order, right? I mean, this order of D at Q by definition is D of Q. That's these are different notations, but the same. So now any F belonging to L of D plus Q has a local expression. Local expression of the form h of z over z plus.
Professor, is it L of D plus Q over L of D?
Sorry,
Isn't it L of D plus Q over L of D?
L of D
Plus Q.
plus Q, you mean?
Yeah.
It should be the other way around?
I think so.
Or this is less than that. It means that this is subspace of that. For L, it's the other way around. Oh, no. You're right. You're right. Yes. L of D plus Q. Very good. L of D plus Q divided by L of D. In fact, I have this L of D plus Q also. I wrote it, I believe. I hope I did write it correctly. Let me check. Yeah, I just wrote it correctly. Here, I just made a mistake. Okay, yeah, cool. So it has a local expression of the form f of z equal to h of z.
Is there a reason why we're using uppercase Q instead of lowercase q for a point?
What's that?
Is there a reason why the notation is uppercase Q instead of lowercase q?
Not really.
Oh.
No, I mean, you can just use little q. That's okay. Yeah, because yeah, you're right. We used that little t before, so yeah, that's right. Actually, it's better to put t here. Yeah, I was just too lazy to change the notation. Okay, so it can be written f of z equal h of z over z to the power n plus 1 with h holomorphic at 0. So then the map f to h of z, h of 0, sorry, defines a linear functional from that big space from L of B plus Q to C, whose kernel is exactly L of D. Okay, so do you see why this is the case? Let's see. I mean, so we are given one point Q. We just use local coordinate Z that maps Q to 0. So we just work around 0 in local coordinate. Then you can write f of z as h of z, which is h is holomorphic divided by z to the power n plus 1. Why that's the case? Why that's the case? Why we can write f in that form? You see, here, first of all, we know that f belongs to L of D plus Q, right? So what does this mean? It means that at Q, and we know that the order of f at Q is m, right? So at Q, this guy must have, because the condition f belongs to L of D plus Q, it means that f at Q, I mean, order of f at Q, right? Let me write it like this, order of f at Q plus order of this guy, which is m, has to be bigger than or equal to 0, right? Has to be bigger than or equal to 0. So it means that the order, okay, so it just means that the order, okay, so let me write it here. So order of f at Q is bigger than or equal to minus m. So if you multiply this by z to the power n plus 1, then it cancels that pole and becomes a holomorphic function at Q. And which is locally h of z.
Yeah.
Sorry?
Wouldn't it just be Z to the
M, Z to the M plus 1. Because you see, this guy has a pole of order n plus 1, m or smaller.
Right.
Okay, so if you multiply it by z to the n plus 1, it becomes holomorphic locally. And that's. And for that function, we pick h of 0. We define a linear function. So. And the kernel of that is exactly the ones that have, actually, they are okay at Q. So this is the second statement is clear. So we get this map here.
What's a linear function?
Sorry.
What is a linear function?
So if you have a vector space, a linear function is an element of the dual vector space.
Okay.
You know the dual vector space, like V star.
Yeah.
It's a space of all linear maps from V to C, from the ground field. Yeah. It's in physics they are called covectors. Yeah. Yeah, and people, physicists could use these things without knowing what a vector space is. Without knowing vector space, they work on vectors, covectors, tensors, all ranked tensors, everything they could work with it without knowing what a vector space is. Okay, so that's what it is. So now what we have now is the following. So we've got a map from L of, so let me write it here. Equals U. There's this linear map into this, and its kernel. Well, I don't know what this map, how to call this, maybe T, and kernel of T is equal to L of D. So these two things, of course, implies that L of D plus Q. I mean, this means that this is space. I mean, the kernel of a linear map is either has codimension at most 1. That's what it is. This is simple linear algebra, right? L of D plus Q. Sorry, it means that dimensional L of D plus Q divided by L of D, yes, is less than or equal to 1. It could be that the map is actually 0. In that case, is everything. The kernel is everything, so there is no difference as codimension 0. Or it could be the codimension 1. That's it.
Why is the kernel L of D? I don't.
Yeah, so what is the kernel? It means that this function has a 0 at least at that point. So if it is 0, then you cancel with this 1 0 here. Then you have a pole of order at most M, so it means that it belongs to L of D. So it's okay at that point. All right, good. Okay, so now we have that. So this is one statement.
How do you cancel?
Sorry?
How do you cancel? If you have a 0 at Q.
Well, if you write it in this coordinate, it means that h of 0 is 0.
Right. Okay.
There's a factor of 0 because h is holomorphic locally.
Right.
And we are just working around that point Q. We don't need a holomorphic function on the whole X, which they don't exist. Okay, so now what about the second statement? It's also a kind of nice choice in that case. So for the second statement, now we wanted to show that in fact omega of D divided by omega of D plus Q dimension of this space again is less than or equal to 1. So why is that so? So we have to define again a linear map. So the linear map works like this. For any omega belonging to omega D, similar to before, for any omega belonging to omega D, we have a local, okay, so not for any. I say any omega belonging has a local expression again, in local expression, which is of the form omega, which is h of z, z to the power m, dz, where h now is holomorphic at 0. H is only locally. Everything depends on choice of local coordinate system, right? Is only locally holomorphic at 0. I mean, this comes from the fact that, okay, what does omega belonging to omega d means? It just means that the guy is like this. I mean, divisor of omega at q, for example, plus divide plus order of omega at q, maybe let's just put omega at q plus order of order of q at q, right? Has to be bigger than or equal to 0, but this guy is m. It just means that this function, whatever it is, locally is a meromorphic function times dz, has a 0 of order at least m at that point because of this condition. So that's why you can write it like that, right? Good. So then the map is completely dual to that, but it's kind of important to omega to h of 0 defines a linear map from omega of d to c, like t, whose kernel equal to omega of d plus q. Okay, so we are done. I mean, the second lemma, second part of the lemma is proof in both cases for meromorphic one forms and for meromorphic functions. So that's proof. Okay, now we want to prove the main thing that the goal of these two things is to prove finiteness of this space of meromorphic functions and holomorphic one forms. So that's the thing we have to do now. So can I erase this? Okay, so now part 3, dimension of L of D is less than infinity, and dimension of omega of D is less than infinity for all divisors D, right? For all D belonging to divisors of X. Okay. So how can we prove this? So proof of this, we just use the previous lemma. So this relation that we had, dimensional L of D plus Q divided by L of D less than or equal to 1. This means that this either both of them are finite dimensional or both infinite dimensional, right? This implies that is that right? Yeah. What am I trying to say? Yeah. Yeah, I think that's a correct statement. Either both. I mean, if okay, it's not what that's not the way I want to say. That's not the best way to say this. I mean, that's true. Either both are finite dimensional, or if one of them is infinite dimensional, the other one is also infinite. But that's not the way I want to say it. How did I? Okay, so. Okay, so let me put it this way. This implies that L of D, quotient L of D minus Q is also less than equal to 1, right? We can do it, we can do that. So we can just go down. We can just go down one by one and then I mean not one by one. Just let's look at L of D minus Q for now, right? Less than equal to 1. Okay. Are you okay with this? Do you know why this is true?
No,
Yeah?
no, I don't know, it's true.
No. Anyone knows why this is true? This is a statement I wrote.
You just said that we need to replace D by D minus Q, no?
You just take D to be D minus Q because this is true for any divisor. So just take D to be D minus Q. That's fine. Okay.
Dimension.
Huh?
Dimension of this.
Oh, this is dimension. Yes. It's the dimension of C. Yes. Okay. So then what we do, we are going to subtract. So the next step, we just write dimension of C, L of D minus Q divided by L of D minus Q minus P. So, okay, so let me put it like this. Another point is less than or equal to 1. So by subtracting finite number of negative points, finite number of divisors of the form. Okay, I mean, basically the sum negative pi, I from 1 to n, but these are just negative numbers, and pi is belonging, distinct points belonging to Q, if you want, belonging to X. Right? So we can bring this divisor to a negative divisor. We can turn it into a negative divisor. We obtain a divisor. With negative degree.
How do we? Because,
Huh? Yeah.
L of D minus finitely many plus 1 over L of D minus finitely many is less than or equal to 1.
Yes.
But how do we get something less than or equal to 0?
Did I get less than or equal to 0? No. I said the divisor with a negative degree. You see, what is the degree of this divisor when you subtract degree as degree of D and then Q and P? So for example, if degree of D is very positive, you just subtract some finite number of points. Actually, you can take 1 point even many times. That's okay. You don't have to choose different points.
Degree of D is 10. If you subtract off 11 points, you get something negative.
Yeah, exactly.
Oh.
And in fact, I'm saying you don't even have to take the new points. You just take the same points. So you just take minus 11Q, and then that will give you a negative divisor. The divisor with negative degree. Excellent, very good. So once you do that, then you get a divisor, which is at the end of the chain, you get a divisor D prime, such that degree of D prime is less than 0. But we know that the dimension of that space of that divisor is, what is it? Is 0, right? So, and dimension of L of such D prime over C is equal to 0. So then you can, and you reach this bottom of the chain at finite number of steps, then you backtrack one by one, you go, and then you see that this is finite.
Why? Imagine if I of D prime 0.
Oh, because I proved the theorem that if you have a divisor whose degree is negative, then there are no meromorphic functions in L of D. So the argument is easy, but you have to know what you're doing. So you just go one by one, and that's it. Just okay. So we use this fact, which is true in general. and this fact.
See,
Sorry?
You get d plus q by adding finitely many points to d prime.
For subtracting.
No, d prime is by subtracting.
Oh, yeah, but then you go backward. Yeah. That's
Okay.
That's right. You can do it that way. Yeah. You can think of it that way. Yes. Now, what about for the other one?
So d plus q and d prime are both finite, and d prime is 0.
Exactly.
Okay.
D prime is not
The
zero.
dimension of d prime.
Dimension of L of D prime is, again, syntax. Yes. Okay. Very good. No. Thanks for asking, for insisting on clarifying things. That's great. So now let me look at the other one. So we have y dimension of dimension over c of omega of d is less than infinity. Okay, in this case, what we do is the following. Now we know that omega of d, we know that dimension of over c of omega of d divided by omega of d plus q is bigger than or equal to 0. Oh, again, less than or equal to 1, sorry. I was thinking about something else now. Okay, so this is space is at most, this quotient space at most one-dimensional. Yes. And we have one more result. Also know that a dimension of omega d is equal to 0 if what? When there was a condition. This omega of d, there are no metamorphic form in it as soon as degree of the divisor is bigger than or equal to 2g minus 2. Right?
Negative either. Negative chi.
Negative Euler characteristic, exactly. So this is 0 if degree of d is bigger than or equal to 2g minus 2. Okay, so then in this case we have to go upward. We have to what do we do in this case? So degree of d is bigger than or equal to 2g minus 2. I know this. I want to say that this is finite dimensional. Well, we just continue the chain. I mean, we just like omega of d plus q. I mean, dimension of this over omega of d plus 2q, for example, is less than or equal to 1, etc. So you add enough number of points such that this becomes a divisor of degree bigger than or equal to 2g minus 2. And we can do that by applying just this, adding multiples of it. You see, well, the reason is that degree of d plus k times q, is equal to degree of d plus k times degree of q. But this is 1. So if you choose k large enough, you're going to surpass 2g minus 2, right? If for k large enough, and that's all we care. So so there is some index k such that omega, and then this is less than or equal to 1. Okay, so we get this is 0, so this is less than or equal to 1, less than or equal to 2, and then it's finite. So okay, backtrack. So that's should I write this down in plain English or is it okay? I think it's okay. You saved me writing that. What's that?
You can write it down.
Okay, sure. Yeah, so choose k belonging to n such that degree of omega of degree of d plus kn I'm sorry, D plus K, yes.
Plus KQ,
Huh?
D plus KQ.
KQ, yes, okay, good. The KQ is bigger than or equal to, or bigger than 2G minus 2. Hence, omega of D plus KQ is equal to 0. Now, okay, so you just write this thing, you continue the chain, you go upward this time. I guess it's similar to the last thing. Now, so let's say omega of dimension of omega of D plus K minus 1 Q divided by omega of D plus KQ less than equal to 1, and this is equal to 0. This implies that dimension of omega of D plus K minus 1 Q is less than equal to 1. And by, I don't know, should I use the word induction or something? Okay, by induction, I just and continue. And then you get that dimension of omega of D plus K minus 2Q is less than equal to 2. And finally, you erase all these things, you get K minus K equal to 0, and that's a dimension of omega of D is less than equal to, I don't know, K or something. Yeah, okay. K is less than infinity. So this proves finite dimensionality of these. This is the most important spaces for us. Space of meromorphic functions, which are sections of this line bundle, and the second one also are sections of a line bundle, but that line bundle needs a little more elaboration because it's a tensor product of a canonical line bundle with a given line bundle. So, and there is some Serre duality there, which I will discuss at one point soon. So that's, but this is very important, very important. And again, I emphasize the caveat in this proof is that it relies on this triviality theorem, which relies on the existence of one meromorphic function on thing. And but for algebraic curves, that's not the problem. That's why algebraics can cheat all the time. Everything is easy for them. Just let X be a solution. I mean, and analysts have to kill themselves to find X. Up to 10 decimal digits, for example. Let X be a solution. They never even ask if there is a solution. Sorry about the rant on algebra. Well, if you stay with me, you will get more rants or less. Okay, guys, thank you very much. So I think I should delete these things from my video. So otherwise I'll get some. No. I mean, that's.